Hello again, class. It's Professor Rourke. I have a few good questions from our section 3.7. And so 3.7 is kind of a nice change in pace in some ways because we finally don't have any more derivative rules being thrown at us compared to some of the ones we've done in the previous sections. The derivatives that we have to take in section 3.7 are like nothing compared to some of the painful parts we've done before now. However, there are still some tricky parts that I definitely think are worth going over, depending on how well you sort of understood the notebook for this section, the textbook, and the corresponding notes. Some of these you could probably just use like a little bit more help here. Okay, so first things first. The question number 1 says a graphing calculator is recommended, which isn't always the best start, but sometimes that means your numbers can get ugly. Sometimes it means they'll be fine. So it's kind of hard to say, but we'll have a graphing calculator handy just in case. Okay, so the question says a particle moves according to a law of motion, S equals F of t, where t is greater than or equal to 0. And where t is measured in seconds and s in feet. And it says if an answer does not exist, enter DNE. Okay, so pretty much again, what they're saying is that there's some particle and it's moving. Okay, and this is essentially like a position function, right? And so this all still ties back to a lot like some similar questions at the end of test 1, where we just sort of started learning how to find the derivative, and how if you took the derivative of the position, you get the velocity, right? The change, instantaneous change in the position is the velocity. Okay, so first things first, it says find the velocity in if feet per second at time t. So it's really like it's asking you to find the velocity equation. It says v of t equals, and then we have to kind of go from there. Okay, so what we'll do first is go ahead and find the derivative of f of t. You can also like call it s if you'd like. Okay, so I'm just going to copy the equation on the right-hand side. So again, said f of t is 2 cubed minus 9t squared plus 24t. And then if we want the velocity is going to be equal to the derivative of that equation, which again isn't too bad compared to some of the other things we've taken the derivative of. So we would just use some simple rules and say 3t squared minus 18t plus 24. Yay. Okay, so first things first, again, we'll just go ahead and type that on in there. Okay, so we'll say 3t squared minus 18t plus 24. Yay. Okay, next question says, what is the velocity after 1 second? So for this equation, we have the velocity, so that's good. So we can just go ahead and evaluate the velocity equation at 1. Yay. Okay, so we have 3 times 1 squared minus 18 times 1 plus 24. Okay, and then I guess like in theory, you don't need a graphing calculator, but you could use a calculator in general. And I think that comes out to be 9. Okay, so that's nice. I have now, by my mouse, 9. And this would technically be 9 feet per second. So just be on the lookout, making sure that like in theory, like on a test or something like that, that we're always labeling the units for these type of problems. Okay, next question says, when is the particle at rest? Okay, so this was the first question that I had some people ask. And so hopefully it makes sense that when the particle's at rest, the velocity is 0, right? That's the key component here. So they don't tell you explicitly, like, set the velocity equal to 0 and solve for t. But if the particle is at rest, then the velocity equals 0. So we can set our velocity equation equal to 0, and then we can just solve for t, right? Hopefully that makes sense. Okay, so remember, this was our velocity equation from part A. And so we can set this equal to 0, and then we solve for t. Okay, so we haven't really solved many equations like this in a while. This is a quadratic, right? So we can take out a greatest common factor of a 3, and then we can check to see if it's factorable, which I think it is. For this equation, we have t squared minus 6t plus 8. So two numbers that multiply together to give me 8 and add up to be -6 would be 2 and 4. Okay, and then we'd say t minus 2 equals 0 and t minus 4 equals 0. So we have 2 times 2 and 4. So that's exciting. Those are my 2 times that my particle's at rest. Okay, so hopefully that makes sense. Again, whenever it asks you for where it's at rest, we can take the velocity equation and set it equal to 0. Okay, so then the next question says, when is the particle moving in the positive direction? So I know this is sometimes where we kind of have to think about like this particle again that supposedly is just moving, I don't even know, like back and forth, right? Doesn't even say, but in the positive direction means that the velocity is positive. I hope that kind of makes sense. So what D is really saying is that the velocity is going to be greater than 0. So really what we're doing is we now are solving a like quadratic inequality. Which, if you recall back from the first section, they're like, I don't know, they're a little trickier than you would think. They take a little bit more work than you would think. So we already know these two like boundary points. We already know from part C that it actually equals 0 when t equals 2 and 4. So really what we have to do is, again, we can do this a few different ways. Option 1 would be to think about a number line, okay? And we have our two boundary points. The boundary points are just what we already solved, okay? What we already solved for, where they actually equal 0 was at 2 and 4. And then you can pick other points in between these boundary points to figure out if they're positive and negative, okay? So for instance, I'll evaluate the velocity at 1, I'll evaluate the velocity at 3, and I'll evaluate the velocity at 5. And all I care about, again, is if it's positive or negative. I don't really care what the number is. I just care if it, again, is positive or negative. So it's not as bad as you might think. One option you could do is to actually use the factored form. Sometimes that can sort of save some time if you're solving these by hand. So for instance, if I plugged it into the equation 3 times t minus 2 times t minus 4, and then I just use that factored equation and enter in 1, you could see that you would have like 1 minus 2, which is negative, and 1 minus 4, which is also negative, and a negative times a negative is a positive, right? So that's one way you could do this, again, without having to actually like slog through finding the numbers. Or, there's lots of options. You could go to your graphing calculator, you could type in the velocity equation and then just use the table of values. You could even type in the velocity equation and just look at the graph and visually see when it's above or below the x-axis, right? So a lot of different options that you've probably seen at some point in time for solving these inequalities. So really just kind of go with whatever one you want, all right? And then again, it says to enter your answer in interval notation. So really I'm looking for, again, it's in the positive direction. When I entered my plug tested points in, that would be between 0 and 2 and 4 to forever. So the way I'll write that, we'll go ahead and say like from 0 to 2. One thing that is sort of interesting about these particular problems that I know can be like a little like tough to kind of think about is for this problem, you might notice I put a bracket on the 0. And so technically at 0, like what is 0? That 0 time, there's nothing going on. But in theory, like theoretically, if I actually like used 0 as one of my like time values, which again, does that really mean? I know. So if we had that plugged in 0 into the velocity equation, we would get positive 24, and that's positive. So that's why I included 0, which again, I know it was a little funky. It's technically because in the beginning they said t is greater than or equal to 0. So that's why I'll include 0 as in the positive direction, even though I know it's kind of weird to think about what that would really look like. Okay, so I hope that makes sense. All right, then it says this next one. This is one I wanted to definitely make sure we talked about because there's a question like this, like on the checkpoint, and there's also a question like this. I think it's on the checkpoint. There's one on the checkpoint or the test, something like that. This definitely comes up. This whole diagram idea, which again, it feels a little weird. I'm not gonna lie. It's just like, what is a diagram? Like, how many diagrams have you drawn in math before? Probably not that many. So we'll go through what you want to kind of have for a diagram for the motion of the particle. Okay, so part E says draw a diagram to illustrate the motion of the particle and use it to find the total distance traveled. Okay, so this is the thing. Essentially, this particle is going in the positive direction for 2 seconds, and then it's going back in the negative direction for 2 seconds, and then it's going positive again. So we don't want to just find like what the position is. Let me get rid of this. After 6 seconds, if we did the position after 6 seconds, that wouldn't tell us the total distance traveled, right? Because like essentially it wouldn't, it would subtract away the distance that it covered when it was going in the negative direction, right? So this is this is what we do, which again I know is a not it's just I don't know. It's just not very common for what we're gonna do. Okay, so long story short, what we do is I usually just draw like kind of one number, okay? And this number line is just for representing the position. Okay. And there's really no like y-axis here, which again, I know is just like kind of like, oh, it feels a little weird, but that's okay. All right. So what we're going to do is we're going to find the position at 0 seconds. Okay. So we're talking about the position, not the velocity equation, right? So the position function was that original. I'm just going to write it here because I kind of scrolled past this at this point in time, which was t cubed minus 9t squared plus 24t. Okay. So first things first, what I'm going to do is I'm going to just find out what the position is to start out with. So when t equals 0, if I plug in 0 into the position, I'm at 0. Now, in theory, we already looked before, like we were supposedly already moving in the positive direction right at 0. Like as close to 0 as you could possibly get. We're already moving in the positive direction. Okay. So there I am. And then what else do we know? The next one we're going to plug in, we know that we're moving positive from 0 to 2. So I'm going to pick 2 to plug in to evaluate at the position. Okay, so when t equals 2, we're going to plug in the t equals 2 into the position function, and that would be like 2 cubed minus 9 times 2 squared plus 24 times 2, which is 20. Okay, so again, you can use your calculator if you want to, it's all good. All right, so the diagram is really just meaning that like we're kind of like pretending like we are the particle and the line, we're representing the line for the particle. And so we're going to say that we're going to connect the dots between 0 and where we put t equals 2. And again, we sort of look like we went to 20. Then we know that we move backwards, right? At t equals 4, if we plugged in t equals 4, I'm not really sure how far I'm going to go here. Do I go into the negative direction? I don't know. But when t equals 4, the position, let's see, this would be 4 cubed minus 9 times 4 squared plus 24 times 4. This is 16. Oh, so it doesn't even really go that far. Okay. Doesn't move that far back into the negative direction of things. And then last but not least, like in theory, like I know I'm now moving positive again, but I'm supposed to plug in like up to 6. Okay, so now I'm going to plug in t equals 6 into my position equation. And let's see, 6 cubed minus 9 times 6 squared plus 24 times 6, 36. Okay, so it starts moving again in the positive direction. And this is, I'll put this point here for like around roughly the position of 36. So it's a bit odd. I know, like I remember when I first, like I honestly don't remember drawing a diagram like this before I taught this textbook, but I was like, okay, we could do this. And so ideally, the whole point is just so that it's a better idea of like really tracking again the distance traveled, not just the position. So because if we plugged in just 6, we would see 36, that the position that particle ended at 36, but that's not the total distance traveled, right? Because we know it went into the positive direction, then back into the negative, then back into the positive. So what we can do, essentially, we're just taking the absolute value of each of these distances and adding them up. Okay, so like essentially from 0 to 2 seconds, the particle traveled 20. Okay, and then from 2 seconds to 4 seconds, it went from 20 to 16. So really it went like down 4. So you could think about it as like the absolute value of -4, or you could just say +4. Okay. And then from 4 to 6 seconds, it went from 16 to 36. So it went another 20. Okay, so really this is just 20 plus 4 plus 20, which is 44. Okay, so if we just plugged in the actual position time into the position, it would just tell us the position. It wouldn't tell us the distance. Okay, so again, I remember the diagram thing. I was like, I don't know about this, but it's fine. It's not the end of the world. And it doesn't really have to be, I think what kind of got me, I was like, how like detailed or exact is this supposed to be when I first started doing this? And it doesn't really have to be anything much. There's no y-axis, okay? It's just supposed to be like sort of a quick visual to help you represent where the particle is moving forward and backwards to help you to get the distance in a like visual, conceptual way. Okay, so hopefully not overthinking it. All right, next up, the part F says find the acceleration, which we can do that because remember, the derivative of the velocity is just the acceleration. So that is something, again, that is important that we want to start feeling very comfortable with, is that if we start with the position function, okay, and we take the derivative, we end up in the velocity. If we take the derivative of the velocity, we'd end up with the acceleration. In theory, we're going to start moving in the other direction at the end of class, okay, where you can go from the acceleration to the velocity and the velocity to the position. But for now, we're just moving down, right? We're just finding the derivative again. So remember, the velocity equation was 3t squared minus 18t plus 24. So I can just find the derivative of that and it'd be 6t minus 18. That was not so bad, right? But again, that concept, you really want to make sure that like makes sense, hopefully. So that's a big one. That's the biggest one. Okay, then it says find the acceleration after 1 second, which is fine. I can definitely do that. I can just plug in 1. And it looks like I have 6 times 1 minus 18. So 6 minus 18 is -12. Okay, so what this actually means is like in my mind, I think of always think about like driving a car, but I know things can be much more complicated than that. But really, like at 1 second, remember just a little reminder because it's going to help us with the next part. At 1 second, we would have been moving forward, right? But we were getting ready to stop and then start moving backwards. So like in theory, there was some kind of like brake being applied. The acceleration that was like working against the velocity, and that's going to be important with one of the last questions here. Okay, is when the acceleration is moving together and when it's moving opposite of each other is very important. Okay, the next one asks you to graph the velocity acceleration from 0 to 6. So let's just like kind of revisit again where we started. So this original function was a cubic function. Okay, it looks like it should start at 0. I know, just kind of thinking of all the things I know. The position starts at 0, and then again, it's cubic. The velocity equation should be starting at 24 and is like a quadratic shape, right? It's supposed to be like at the velocity is supposed to be 0 at time t equals 2 and t equals 4. It's like should be above the x-axis from like 0 to 2, and then below the x-axis from 2 to 4, and then again above the x-axis from 4 to infinity. And then also the acceleration should be like a linear equation with a positive slope starting down at -18. So that's a lot going on between all of these things, and we can sort of just use like all of that information just ties in together to be able to help pick out what graph this is going to be. So for this first graph, for instance, it looks like the position starts at 0. Okay, that then looks mostly cubic. It could be it. The velocity is quadratic, and it looks like it's positive between 0 and 2 and 4 and infinity. That could be it. Oh, the acceleration looks like it's negative and it's starting at +18. So that is not going to be the one we're looking for. We want the acceleration to be down, like essentially just like the negative, same y-intercept, but negative and a positive slope, right? I'm just basing it off of these equations. Okay, so let's take a look at the next option I have here. The position function maybe looks okay. Velocity looks good and acceleration looks good. I think this might be the graph we want, but I'll just kind of make sure I check the other ones to make sure. This third graph option for me has them all just kind of screwed around, like where like the velocity is actually the what's supposed to be the position, the position and velocity are switched, and A is wrong as well. And then the last one, A is correct, but again, the position and the velocity are switched. So that's why we're going to go with the graph that the position starts at 0, it looks cubic, the velocity starts positive, dips down below, and then comes back up after 4, and the acceleration should just be a line, okay? And so we can also tell like the acceleration is 0 at time t equals 3. They didn't even ask that, but just in case, I don't know. So it's negative acceleration from 0 to 3 seconds, positive acceleration from 3 to infinity. Or you could talk about like all day about these graphs. I feel like there's a lot of things you could say, depends on kind of what they ask. But this is the kicker. It says, when is the particle speeding up and when is it slowing down? Okay, so I'm going to go back to my graph and to help me answer this. But if you don't have like this whole spaghetti curve looking of graphs, there's other ways to do this. Okay, so the main idea is kind of what I mentioned before when it was like, what is the acceleration at a certain time? I think it was 1 second, right? And so for instance, at 1 second, if we look at even this graph, the velocity is positive and the acceleration is negative. So what that means is when they're opposite like that, they're working against each other, right? So we are slowing down when the velocity is positive and the acceleration is negative, or vice versa. When the acceleration is positive and my velocity is negative, and when my velocity is negative, I'm really moving like backwards. But now my acceleration is moving forward. So they're working against each other. So you can be speeding up into the positive direction and you can be speeding up into the negative direction, right? So I hope that kind of makes sense, the whole speeding up and slowing down things. So I'm going to show you this 2 ways. First, I'm going to focus on just the graph, and then I'll show you on how you could do this in other ways. Okay, so first things first, when we start out, the velocity, I'm ignoring the position for now, by the way. The blue line here is irrelevant. When I start out at time t equals 0, right, from 0 to 2, remember my velocity was positive and my acceleration was negative. So in terms of like organizing this, I'm going to say from like the time, just to help me keep this organized, it can look a few different ways. Between 0 and 2, right? My velocity, just to kind of keep track of my signs, my velocity was positive. My acceleration is negative. So what does that mean? It means I'm slowing down between 0 and 2. Okay, does that make sense? And then let's see what else is happening here. Between 2 and, well, like it's the velocity is negative between 2 and 4, but the acceleration changes signs. Okay, so you really want to focus on all the places that the acceleration or the velocity are 0 and where they switch. Okay, so I'm going to say between 2 and 3, okay, just to kind of, again, keep this organized, my velocity is now negative, okay, but my acceleration is also negative. So that works out really well. I'm flying backwards, okay? So I'm speeding up into the negative direction, but I'm still speeding up. Does that make sense? Like I am accelerating in reverse. No brakes, okay? So that would be between 2 and 3. And then my next important section is going to be between 3 and 4, because again, that is where my velocity now changes from negative to positive. So between 3 and 4, the velocity is negative, and my acceleration is now positive. So again, I'm slowing down again. Okay, so now again, I'm putting the brakes on in theory. There's 2 forces are working against each other, so I'm slowing down. And then at 4 seconds, I've come to a stop. And this is where, let me check real quick. Is this from 4 to infinity? It doesn't even say, just still forever. Okay. So if we're doing this forever, go ahead and line this back up again. This will just be from 4 to forever because there's not going to be any other times, like unless something crazy happens that I don't see on this graph. The velocity does not again reach 0, and neither does the acceleration. And so my velocity is positive after 4, and my acceleration is also positive. So once again, I'm speeding up. Okay, does that make sense? So these graphs can be helpful, but you don't need the graphs if that wasn't like one of the questions. If I don't ask you to graph them, or it just doesn't have the option to see the graphs this way, you could have figured this out just with some like number lines. Really, the only thing we didn't have that this graph did tell us was when the acceleration was 0. So if you would did this by hand, right, you would have to find when the velocity equals 0 and when the acceleration equals 0, right? And then this is when we would like set up a table of signs, just like we did here. Okay, so for instance, if we didn't have the graph, we would still have 2 and 4 from from the velocity, and then we would still have 3 seconds from the acceleration. So we would still be able to set up, okay, I need to find something between 0 and 2, and then 2 and 3, and then 3 and 4 is my last one, so 4 for forever. Okay, those were still like the key intervals that you would then use to set up your signs. Okay, so now I'm going to answer the question. When is the particle speeding up? So again, that is when the two of these are working together. So they're speeding up between 2 and 3, and then 4 to infinity. So I'll go ahead and fill that in now. We'll say 2 to 3. Oopsie daisy. I can type 2 to 3, or 4 to infinity. Okay, so I hope that helps make sense a little bit. Next one is when is it slowing down? So again, I kind of find both of these together because it's slowing down from 0 to 2, then again from 3 to 4. Okay, so again, because of the whole 0 thing being kind of an odd one, like really I know it's sort of unusual to have it like included like that, but it's only because it says that t is greater than or equal to 0. And for both of these, it would still also be slowing down because at 0, the velocity would still be positive, and at 0, the acceleration would still be negative in theory if it had started right at 0. Okay, and slowing down from 3 to 4. Okay, so again, I hope this helps. I know that was a long problem. This was only 6 and this homework, but especially I wanted to make sure we talked about that diagram and how we figure out this slowing down or speeding up. Those are really the new things that are featured in this particular type of problem that you do want to feel comfortable with. So again, this was from 3.7 and a lot of big ideas that hopefully you can let me know if you need any help. I would be happy to help answer them. Okay, thanks class.